Good evening. All right, we have a small group today. Let's see what we have online. There's a way for me to All right, I'll check back at some point in case there are any questions from online, although I won't find out about it immediately, but I will check it before the end of the All right, I'll check back at some point in case on today to analysis of continuous variables with correlation and regression. This is chapter 7. Sections. Linear regression, Pearson's correlation, and coefficient of determination, parametric alternatives. Just to do a quick review, for the methods of inference that we have learned, these have been for two variables, and both descriptive methods and inferential methods. And we thought of one variable as the response or outcome variable, and one as the predictor. This is not the case for, say, the chi-squared test, but this is the case in regression, and we'll have the response or outcome on the y-axis, and the one that we're sort of hypothesizing is caused by something on the x-axis, the predictor. Even when causality is not known, but we have some hypothesis about the causality. In the case with two categorical variables, we did inference using the chi-squared test. There are other options, but we won't really get to those until future semesters. For now, we're just saying the chi-squared test for categorical variables, and for inference, and then for description, contingency or frequency tables, and odds ratios or risk ratios in the case of two binary variables. The example we did last class was the race and the death penalty, and doing description and inference about whether there was any difference in the rate of death penalty verdicts between high race and the defendant. In the case of two variables where the response is continuous and the predictor is categorical, we can use the t-test. If that predictor is binary, or analysis of variance, where that predictor is categorical, we can use statistics or visualizations, box plots and bar plots. So we're moving on today to this special instance of two continuous variables in bivariate regression, so just one response and one predictor where they're both continuous. And for inference, we will cover regression analysis and using scatter plots for description, such as these two little examples. So, just to give a few example kinds of applications where this might come up with. This first example is one of studying any relationship between water disinfection byproducts and immune T24 cells. And this is kind of a complicated abstract. There's a huge number of abbreviations in it. But I just did a PubMed search for Pearson correlation. For all the complicated stuff in here, you see that just Pearson correlation analysis was used to show that cellular GSH levels, so this is some measure of the response in the participants, is inversely correlated with ROS production and cellular GST activities. So we're not knowing anything about what all of these things mean. We know that what this means is this is some continuous measure, cellular GSH level, presumably that is the contaminant, and it's inversely associated with these biological activities. So when you have higher GSH level, you have lower RSH production and lower GST activity. So that is the kind of thing that Pearson correlation analysis tells us. The second example here, this was a validation of the quality of life in life-threatening illness family care version. This is a quality of life qualitative measure based on a questionnaire, German-speaking carers of advanced cancer patients. This, I believe, all this paper was about was validating a quality of life score, where there was a questionnaire given to the participants that are all related questions that are supposed to tell you something overall about patients' quality of life. So I'm just looking at the results here. Pearson correlation between test and retest lay at 0.92. So this is a high Pearson correlation that tells you that when you give the test to the same people 2 times, you have high correlation between their scores in those 2 tests. The maximum here is actually 1, so 0.92 tells you that it's very closely related if you give the same test 2 subsequent times. And there's a significant positive correlation with hope. So that means that the score, the higher it is, the higher the person's level of hope. And significant negative correlation with traumatic stress with an R of -0.41. So that means higher score, lower traumatic stress. So generally it seems that a high score is good. Depression, R equals -0.51, anxiety, R equals -0.52, and overall subjective burden, whatever that is. But clearly, so this, all of these negative correlations here tells you that a high score means you have lower amounts of traumatic stress, depression, anxiety, and subjective burden. Or conversely, a low score means you have more traumatic stress, depression, anxiety, and subjective burden. So you can kind of start to get an idea already here of why this is such a popular measure. It's a simple number. It goes between -1 and 1, and it tells you what kind of relationship exists between 2 quantitative variables and how strong that relationship is. Final example application, folic acid supplementation on homocysteine levels in children taking anti-epileptic drugs in a randomized controlled trial. So this trial set out to assess the level of homocysteine in children taking anti-epileptic drugs and study whether daily oral supplementation of folic acid for 1 month will reduce their THCY level, homocysteine levels. Skipping through the materials and methods, the key part of the methods for us here is that correlation was tested by Pearson correlation, and p-value less than 0.5 was taken as the cutoff for statistical significance. This is a very general materials and methods they gave. They also said statistical significance was tested by chi-squared test, and paired and unpaired t-tests is appropriate. So can't really tell what they used where here, but they've done a bunch of different tests. Apparently for 2 categorical variables, 1 categorical, 1 quantitative, and for 2 quantitative variables. All right, so let's look into it a little bit more deeply. We have an idea of what the motivation is for this measure, that we sometimes have two quantitative variables, and we want a simple both description of the strength of relationship and direction of the relationship, and we would like inference about whether a relationship exists. So scatter plot, you're probably familiar with, is a good visualization of two quantitative variables where you just plot the x and the y values. Correlation quantifies the strength of the linear relationship between two variables, and only the linear relationship. So no other kinds of relationships are completely captured in correlation. And when I say correlation, this only has to do with the pattern of the values and whether they tend to high together and low together, or whether there's no relationship between the two, or a negative or an inverse relationship. It's not about causality. There's causality more towards myself. So just a few examples. Here are a couple of linear relationships: positive linear relationship, -1, and a couple of non-linear relationships. Here's one there where there's probably no linear relationship at all, just this parabola. And here's another one where there again may be no linear relationship, but if you only have these data points, there's no positive correlation. The values of x and y are tied together or together. In a strong relationship, the value of either x or y tells you most of what there is to know about the value of the other. And in a weak relationship, there is a lot more. There's a lot more uncertainty based on knowing one or the other. So the weak relationships, knowing x still tells you something about the value of y, but not as much. You can imagine that if you know x is right here in the middle, there's this fairly wide range of y's, whereas over here, getting the value of x, there's a fairly narrow range of y's that you find. And here are a couple examples of no relationship. One where the variance of x and y are the same, and another one where there's a large variance in x and a small variance in y. But in both cases, there is one relationship. So another way to say that is, and here, the variance of each variable is different, but another word for this relationship is the covariance, and the covariance in both cases. Just to give you one real data example, this is the rates of immunization for diphtheria, polio, tetanus in a number of different countries. The percentage of children under 5 that are immunized plotted on the x-axis, and the under 5 mortality plotted rate on the y-axis. This is the number of infant deaths, I think, per 100,000. So how would you characterize this relationship? Not good? Yeah. There's certainly, it's not all of the variability that you're explaining. There's one data point here that seems to be quite an outlier. There certainly does seem to be a negative correlation. The low percentage immunization have high mortality rates, and most of the ones with very high immunization rates have low mortality rates. know, but if I had to guess, I would guess this is maybe somewhere around minus 0.8 or minus 0.7. I don't know. It's probably interesting to look at what the outliers are. Like, here's one. Greece has a fairly low percentage immunized, only 54%, but also a very low under 5 mortality rate. So I think this country is Greece right here. So I don't know how they manage to do that, but there's certainly some kind of different circumstances here. And on the other extreme, here's a country with about a 90% immunization rate, but a pretty high mortality rate. Let's see, what would that be? China has a 94% immunization rate, and yet still a 43 per 100,000 mortality rate. So presumably there are, well, one thing to consider is that, again, this is a correlation, it's not causation. Surely not all of these mortalities are being caused by diphtheria, polio, or tetanus. Some of this is just immunization as a marker of a robust public health infrastructure. But there can be other causes of mortality. So something like these outlier countries is probably an indication that these are countries that have caught up with other advanced countries in terms of immunization, but potentially not in terms of other causes. So keeping with our convention in this class of using Greek symbols for population and Roman characters for samples, we'll use rho for the population correlation coefficient, and R for the sample coefficient, which is the estimate of rho that we get from a sample. And this R is what we call Pearson's correlation coefficient. It's occasionally called the product moment correlation coefficient, but Pearson's correlation is the most common R. The calculation looks pretty similar to the way that we've calculated standard deviation. In the population, it is simply a ratio of, these are the differences of our x values minus the mean of x over the standard deviation of x. So this is something like a score for each observation, multiplied by the z-score for that same observation using its y value. So for each observation, we have an x value and a y value. It's essentially calculating the z-score for the x value times the z-score for the y value. That gives us our population correlation coefficient. So you can get a bit of an intuitive understanding, I think, from the correlation coefficient from this, in that if there is no relationship between x and y, then the fact that x has a large positive z-score has no bearing on whether y will apply. It's just as likely to be negative. That is the situation with a zero correlation coefficient. Whereas with a correlation coefficient of 1, it means that for a positive z-score on x, you must also have a positive z-score on y. It means that, and for a negative correlation coefficient, it means that with have a positive z-score on X, you have a negative z-score on Y. If you're estimating it from the sample, it's just like with the averages that we did. Instead of dividing it by n as we would in the population average, it's just divided by n minus 1. These calculations are reasonably straightforward for correlation. And just to give you a bit of intuition for what some of them look like, an R of -1 means that there's a perfect linear relationship between them. So a straight line will pass through every single data point. There's an R of -0.6, an R of 0, an R of positive 0.3, and an R of 1. So having looked at a bunch of these was why I guessed that, I don't know, that correlation for the GPT immunization and mortality was maybe somewhere around -0.6. Maybe a little less. So both rho and R are unit free, so it doesn't matter whether you are talking about pounds, about milligrams per liter, or what you're talking about. Because they are ratios of measurements to standard deviations, numerator and denominator have the same units, and the correlation coefficient has no units. Which is a nice property because whatever your units were, we always get values between and including -1 and 1. -1 including meaning perfect negative relationship, and 1 meaning a perfect positive linear relationship. The closer there to 0, the less of a linear relationship is. It's worth noting that unless you have a perfect correlation, then a high correlation does not necessarily mean you have a linear relationship. There was an example I showed before with a bit of a curve, just a bit of a curve in the line that could have a very high correlation coefficient, even though that relationship was not linear. A high correlation also does not imply a causal relationship. It just means there is a relationship that they tend to vary together, but it doesn't mean that it's causal. And just as with means and standard deviations, this value of R is sensitive to outliers. So a single outlier can change R quite a bit. It is not resistant to we can perform inference on the population correlation coefficient rho, with the null hypothesis being that rho, the population correlation coefficient, is equal to 0, and the alternative hypothesis that it is not equal to 0. And this test is carried out under this convenient relationship that when your null hypothesis is true, this test statistic, n minus 2 being the sample size minus 2 over 1 minus the Pearson correlation coefficient squared, its square root times R, is t distributed with n minus 2. So if you know, well, if you have your data, you can just use your statistical software to do a test on the hypothesis test for the Pearson correlation. But even if you did not have that, if you just had a paper that reported, it told you what the sample size was and what the correlation coefficient was, like those abstracts we saw, even if they didn't perform the hypothesis test, you could do it yourself. If you know this formula, you could plug in the Pearson correlation, plug in n, calculate the t statistic and look it up in your table of probabilities for the t distribution and decide whether or not to reject the hypothesis. Yes?
Calculate the confidence interval on
Yes, you can also calculate the confidence interval on row. I don't think I actually have a formula in here. For doing it. But you certainly can calculate a 95% confidence interval on row. Let me take a look to see if that formula is in the textbook. And I can post that for you later. Good question. Probably the more the common way that you get a confidence interval is through regression analysis. If you have the actual data, you can use a regression analysis to get a confidence interval for both on the regression coefficient and on the Pearson correlation coefficient. There are a couple of motivations for regression analysis that are sort of complementary to each other. And I mentioned this only in passing here, but in some applications, I've ended up talking a lot about this, and you actually have to think about what your purpose of the regression analysis is. One of them is prediction. You want a model that allows you to predict your values of y from the given values of x. And the other is about inference and wanting to infer whether a given independent variable has an effect on n. And I would say that in most applications in FE, at least the ones that I see people working on here, the second one is the main purpose for regression analysis. It is for inference between your predictor variable and your response variable. But prediction is a different and sort of complementary purpose. So a simple linear regression model, there's one independent variable x and your dependent variable y. We describe that relationship using the slope, an intercept, and a random error being the component of y that cannot be described by this linear relationship. And I use uppercase x and y for random variables and lowercase with subscripts for the individual observations. So writing out this simple linear regression model, we've got our independent variable y, which is decomposed as an intercept. This is for the population, plus a slope times the dependent variable, and then the random error term for the residual. These are some alternative formulations of it. This first one is basically the same. The second one is a little bit different in that it's describing only the model part, or the systematic part of the model. So this is saying that the mean value of y conditional on the value of x is equal to the linear part of this model. That doesn't include the error. In general, all kinds of regressions somehow include a systematic part and a random error. And it's not always in the form of a residual, but there's always somehow these two components of the part that the model predicts and the part that the model doesn't predict. So that was a population regression model. The estimated regression model looks like this. So I'm now using lowercase values because these are for individual observations. And the model is that a given predicted value of y is equal to this intercept plus the slope times the value of the independent variable for that observation. So this hat means that it's estimated or predicted. And this is a model that we estimate from the data by the method of least squares, where we attempt to fit, or we do fit, a line which is defined by the intercept and the slope, which minimizes the sum of squares of all of the error terms. It's not the only way to fit this model, but it's the first way to do it. So, these terms have interpretations. B0 is the estimated average value of y when the value of x is 0. That's the intercept. And the slope is the estimated change in the predicted value of y as a result of one unit change in x. So if x is in kilograms, it's how much y changes for a change of 1 kilogram. So both of these have units. Going back to the analysis of variance stuff that you learned, it's still relevant here. And the total variation, even though we don't have the categorical predictor here, we can still break up the variation in the y variable into two parts. That is, the total sum of squares of the response variable can be broken down as the sum of squares of the error, the unpredicted part, and the sum of squares of the regression, the predicted part. So an analysis of variance, this would have been broken down again into errors, but this part into the variance of the group. So in that case, do you remember what the F statistic was? It was the ratio of the explained variability, that would have been the sum of squares of the regression, to the sum of the residual variance, or the sum of squares of error. And it actually turns out you can use an F statistic here too. It turns out you get the same inference, whether you use the F statistic or the T statistic. This is linear regression. But usually we do this for another purpose here with linear regression. This is just writing out what I already explained, but that total sum of squares is the variation of the y values around their mean. The error sum of squares is the value of each y value minus its predicted y value, so the unexplained part of the relationship, sum of those squared errors, and the regression sum of squares is the variability of the predictions around the overall mean. So this is how much variability you're predicting, how much variability you weren't able to predict, adding up to the total variability. And I bring this up now not because we're actually going to do analysis of variance again here, but also so you won't be surprised if you see an analysis of variance in a regression framework in the future. It's the same as the analysis of variance that you already learned. But because I wanted to introduce the so-called coefficient of determination, which is the portion of the total variation in the dependent variable that is explained by the variation in the dependent variable. Or in other words, the sum of squares of the regression divided by the total sum of squares. So whereas the F statistic, the sum of squares of regression divided by sum of squares of error, this is divided by the total sum of squares. So whereas the F statistic was usually greater than 1, this is value between 0 and 1. So what is the value of 0 going to mean here?
Yeah, I think that there's no association between the two.
Yeah, there's no association between the two. Or put more mathematically, that there's actually no variability in the sum of squares of regression. So the predicted values of every observation is the same. Your model doesn't predict any variation in y based on values of x. So this numerator has to be 0 in order to get r squared of 0. And r squared of 1.
He explains the independent variable perfectly explains the variation.
Yeah, so it means that your sum of squares of the regression is equal to the total sum of squares. So your variability, going back to here, your variability in the regression is the same as the total sum of squares, which means there's no sum of squares of the errors. There's no error in these predictions. What's the likelihood of that happening? The only case where that is really ever going to happen is through brutal overfitting to your observations. Because in real life, almost nothing is perfectly predictable. And even r squared values of anything fairly high, there's a chance that it is due to overfitting. Not in linear regression, because you're only fitting two variables, but as you start fitting more and more coefficients and more variables, you start having overfitting into a high coefficient of determinant. I work with high dimensional data, which means that you have hundreds or thousands of predictors, and it's very easy to do overfitting, which is why I bring that up now. Because in a high dimensional data situation, I see in R squared, even anything over like something pretty low, like anything over 0.5, and I'm pretty suspicious. They're very cautious. But yeah, linear regression is much more forgiving. So here's your definition of R squared. The sum of squares explained of the predictions, or that explained by the regression, divided by your total sum of squares. In the single variable case, so simple linear regression with just one x, then R squared is equal to the square of the Pearson correlation coefficient. That's only the case in this single predictor case. In the instance where you have 2 or 3 or 4 or more predictor variables, you can still calculate an overall coefficient determination, but not an overall Pearson correlation. Pearson correlation is only the relationship between two quantitative variables. Whereas R squared, this can be done for any regression model where there is a continuous y variable. How many x variables you have, you can calculate the coefficient of determinant.
So the R squared for a multi-variable regression would tell us how much variation in the dependent variable can be explained by the variation in all the variables.
Yeah, it tells you how much of your actual variation in Y is predicted by your model.
By all of the.
Yeah, like if you're looking at this, if you're calculating your coefficient of determination, all you actually need is your observed values of Y and your predicted values Y hat. That's enough to calculate the coefficient of determination. Whether you have 1x variable or 10x variables, what matters is these predictions of the coefficient of determination. Because the variability in those predictions gives you your sum of squares of regression. It's the variance of those predictions around the overall. So it's nice in that no matter how complicated your regression model is, you get into multivariate models, you can have like mixed variable types. You can have a regression model that includes both categorical and continuous predictors. You just still have a single R squared. That's all you need is those predictions and the observed values to calculate. Here's the sum of squared errors, the values of Y minus it's the regression part, the predicted values minus the mean Y, and do this total sum of squares, the observed values minus the overall mean.
I don't know if you want to get into that today, but what's the difference between the R squared and the R squared with a dash of it? Where I believe adjusted R squared.
Oh, yeah, we'll get into the adjusted R squared in the last class, but I'll give you a preview. R squared. If you fit a regression model to your data, that is, you minimize your sum of squares by changing these regression coefficients, you will always get a positive R squared, because even if there's no true relationship between X and Y, they're just sampled from independent normal distributions. Just because of sampling, especially the smaller your sample size, you can fit a line that probably doesn't have an exactly zero slope that will reduce those residual errors a little bit. So even with no true correlation, you'll get a positive R squared. Now, if you only have one predictor like this, it's probably still going to be pretty small, but the more variables add in a multivariate regression, the more you can increase R squared by fitting, or in fact overfitting these data. The adjusted R squared is an adjustment for the number of degrees of freedom used by your model. So as you add more variables to a multiple regression model, R squared will increase as a function of the number of variables. It will always increase. Adding another variable, always just due to random sampling variation, gives you the ability to increase R squared at least a little bit. But the adjusted R squared is a correction for that, such that on average your adjusted R squared does not increase just by adding more variables to it. So again, an R squared of 1, like R means a perfect linear relationship between X and Y, except whether it is positive or negative, R squared is still plus 1. It's always between 0 and 1. That can be interpreted as meaning that 100% of the variation is Y, and Y is explained by variation in X. There's no residual error. Somewhere in between means that some of, but not all of the variation in Y is explained in a linear model by variation in X. And R squared of 0 means that there's no relationship between X and Y. And this, again, this is in a population. This would be R squared equals 0 for any given sample. Even when there's no linear relationship, you'll get some small positive R squared. These are the assumptions in linear regression. The first is that is the assumption of linearity, that the population regression line is straight, so that the true relationship between X and Y is linear. Second is homoscedasticity, that the standard deviation of the error values is constant across values of X. Similarly to the assumption that we made in ANOVA, it is worth saying that there are extensions to linear regression that allow you to do a corrected model case of heteroscedasticity. But in standard linear regression, we're making this assumption that the errors are constant. The difference, if your errors are not constant, it means that that some of your data points are more reliable than others because the residual variability is less. You have some points that have a low residual variance, then those give you a lot of information about the regression relationship. But if you have other data points where there's a large residual variable, those are giving you less information about that regression.
What would be an example of such a population or sample?
An example of, say, where homoscedasticity is violated. I think it can be violated due to non-constant measurement errors. Like there are some measurements that you make that are just more reliable in one part of the range than the other, where like maybe your measurement error increases as a function of the value of the measurement. So you have fairly precise readings for small values and less precise readings for larger values. And if you know what that relationship is, you can model it. You can model by the things that you get to each of those data. But if you don't know what they are, you just have to assume that error is the same for all data points and weight them all equally and assume that the same amount of information about all the regression. I'm sure there are other examples as well of heteroscedasticity. That's just one that pops to mind. We are assuming normality, or at least approximate normality, that for a given X, the Y or the errors are approximately normally distributed. So note this is not quite the same as saying that Y is normally distributed. It's saying that conditionally on X, Y is normally distributed. Why do I make that distinction for a given X? So what I'm saying essentially is that the errors are normally distributed. Well, let's think of an example. Say the relationship between I don't know, height and like, I don't know, height and weight is probably not actually normally distributed since weight is a volume. But probably the relationship between like height and shoe size, that's probably a more or less linear relationship. And also one where height, the whole population is probably normally distributed, as is the shoe size. But if we were, suppose we were to take a stratified sample of what's an example? You know, some strategy that gave us a stratified sample of tall people and short people, then both X and Y can be somewhat bimodally distributed, which would seemingly violate the assumption of approximate normality. But as long as for a given height, shoe size is normally distributed, it's not violated, it's still okay. So that would be an example of where Y is not normally distributed, but conditionally on X it is normally distributed. And that's okay, that's the normality that we're talking about.
And the standard deviation for each of those two distributions would also have to be the same for it to be almost.
That's right, that's right. The standard deviation would also have to be the same. So actually, that's another instance where probably the residual error for the short people would be lower than for the tall people. I don't know. Or maybe not. If it's just measurement error, then it's probably the same. And finally, independence, that each of these observations is an independent observation. So if we accidentally took repeated measurements of the same people multiple times, then we're going to get a biased estimate of our coefficients and also a biased p-value for our inference. One way to express this very compactly is by writing out our regression equation and then saying that the errors are distributed, and in fact, there's a little something missing here. This is often written above the little tilde here, IID, or independent identically distributed. It's saying that every error is independent of all the other observation errors, and they all have the same distribution with a mean of 0 and a standard deviation constant of sigma. So this contains the normality assumption. It's saying that the errors are normally distributed. Like I was saying, it's the errors that are normally distributed, not necessarily the Y's or the X's. That all of those errors have a mean of 0. That if the errors have a mean of 0, that it must mean that the linearity assumption holds. Because if you have a nonlinear term, something not captured by the beta 0 plus beta 1 x, that means that in certain parts of the line you'll have a lot of negative errors, and in other parts you'll have a lot of positive errors. So if this is true, that all the error terms come from the same normal distribution with a mean of 0, then it must be linear. And if they all have the same standard deviation sigma, then it must be homoscedastic. So this contains all these three assumptions, and if we had written independent identically distributed, it would also contain the assumption of independence. So this is sort of a mathematical representation of all of these assumptions. between correlation and regression. So if X and Y are normally distributed with a correlation rho, and the regression assumptions hold, then that coefficient of the linear regression is related to the population correlation coefficient by the ratio of the standard deviations. Population correlation coefficient that varies between -1 and 1 multiplied by the ratio of the Y standard deviation over the X standard deviation gives you the correlation coefficient. And the same thing using the estimates from the sample. So whereas beta is a slope and it has the units of the Y variable divided by the units of the X variable, the correlation coefficient is unitless, but then we again are multiplying by the units of the Y variable divided by the units of the X variable. And these things are so another way to say this is that the correlation coefficient can also be thought of as the regression coefficient for scaled variables. So if both of these variables are scaled so that they have a standard deviation of 1, then the regression coefficients are equal to the correlation coefficients. See what I mean by scaling the variables?
Large enough n?
No, I mean, in the example of, say, height and shoe size, instead of using height in inches or centimeters, we were to scale them to z-scores so that we subtracted the mean and divided by the standard deviations of everyone's heights. Were like positive if they were above average, or the +1 if they were more than 1 standard deviation above average, and less than -1 if they were more than 1 standard deviation below average. But so the standard deviation of 1. And the same for shoe size, then the linear regression coefficient would be equal to the correlation coefficient. The inference is also related. In the inference, and this is why I was saying the way in practice you probably would get if you wanted a confidence interval on the correlation coefficient. This would probably be the easiest way to do it. To do your linear regression and get your estimate for the coefficient and its confidence interval, and then just multiply that by the standard deviation of X over the standard deviation of Y to get the confidence interval on. Or alternatively, scale your variables and do your regression coefficient to get your rho and its confidence interval. But whether you do it, that is to say, whether you scale your variables and then do your regression, whether you use that formula for doing the t-test on rho, or do a linear regression, the results of the inference are p-values when you reject and when you accept the null hypothesis are the same. And if, as I was saying, X and Y are converted to z-score, then your coefficient beta is the same as the correlation coefficient, and the estimates are the same. So that is to say, the population values then are identical, and your estimates will also be identical. Here's an example from your textbook, chapter 7, of body measurements. So the scatter plot, whoops. The least squared summary below show the relationship between weight measured in kilograms and height measured in centimeters of 507 physically active individuals, and it actually does look pretty linear. So much noise it would be hard to tell if it were not. I kind of expected it to be maybe an upward curving relationship, assuming that as you get higher, you also get larger functions as well. So we have, it gives us the output of our regression table with the estimates of the intercept and the slope for height, along with standard errors or t-values. So these are the t-values that we would get if we use that formula from the correlation coefficients, and p-values for getting an absolute value of t larger than or equal to this t-value. So let's talk about this a bit. First question is, describe the relationship between height and weight. How would you describe it? What's that? Yeah, it's a positive correlation. It looks fairly linear. It looks like a reasonably good correlation. I don't know. I would guess an R squared of 0.5 or something like that. Second question, write the equation of the regression line. Interpret the slope and intercept in context. So do you know how to write the equation of the regression line?
The 0.04.
Write the whole thing out. So weight equals
0.04.
Where are you getting 0.04 from?
The intercept on one.
Let's really make this a little bigger.
Weight equals negative 105 plus 1.02 x plus temperature.
So the regression line itself would just be weight equals minus 105 plus 1.02 times height. Yeah. And the regression line doesn't go here. It's just the linear line.
And then for every unit increase in height, we'd expect roughly a unit increase in weight.
And weight. Yeah, exactly. And the intercept?
It doesn't really mean it.
Means someone with zero weight would have a negative height, or someone with zero height would have a negative weight. Doesn't mean anything. Do the data provide strong evidence that an increase in height is associated with an increase in weight? Yeah. P-value on this coefficient under the null hypothesis, the zero estimate is less than 0.0001, so that's strong evidence. State the null and alternative hypothesis.
Null hypothesis with coefficient, the regression coefficient is 0.
Yeah, or that there is no relationship between height and weight, or that the correlation coefficient is equal to 0. Any of those.
And the alternative would be that there is an association or it's not.
Yeah. P-value less than 0.0001. The conclusion is that there is a positive relationship between height. And finally, the correlation coefficient for height and weight here is 0.72. what is R squared? You know, now it's just the square of that. I don't know what 0.72 squared is, but it's pretty close to 0.5. 0.52. So how do you interpret that?
Regression.
So how about in terms of the total variability in weight? The total variability in weight is the variability in individual weights relative to the overall average weight. Total variability in weight is the variability in so this R squared 0.52 means that approximately 52% of that total variability in weight is predicted by variations in height. So our predictions in weight, their variability is 52% of the total variability in weight. So in kind of informal terms, that's often stated as being 52% of the variability in weight is predicted by height. All right. So wrapping up, you can use simple linear regression, coefficient of determination, Pearson's correlation for continuous outcome and continuous predictor. Actually, coefficient of determination is more general than that. You can use it for multiple predictors, categorical predictors, analysis of variance, but linear regression and Pearson correlation are a continuous outcome and a continuous predictor. And values of Pearson's correlation coefficient between -1 or between -1 and 1, and they describe both the strength and the direction of an association between continuous variables. Whereas coefficient of determination, R squared, varies between 0 and 1, interpreted as the proportion of total variance explained by the regression. And there is an equivalence between regression coefficient and Pearson correlation in that the going for the estimates, the estimated regression coefficient is equal to Pearson's correlation coefficient times the ratio of variances, the standard deviation of y divided by the standard deviation of x. And there's an equivalent formula like this for the population values, rho, sigma, and beta without the hat. And that's all we have for lecture today. I went a little bit over time. What I will do now, actually, first I'm going to check if there are any questions coming up online. The sound, uh-oh. Is the sound still, has it been bad this whole time? Is the sound still, has it been bad this whole time? Is the sound still poor? So what I will do now is I'm going to put on a previous recording of this week's lab from Tony in a previous year. I'll put it up here on the big screen and sit here and watch it with you, and so that you can ask me questions as it goes along, assuming that you all want to stay here and do that. You're also welcome to go home and watch it on your own if you would rather do that. But I'm here for the class if there are any students who are also wanting to stick around and do that together. I'm assuming if you made the trip out here, you want to stick around for the full class period. All right. I think we've lost our online people potentially due to poor sound for some reason. So what I will do for the online folks is I will give you a link to this Hangout so that you can instead come here without continuing this recording. Okay, I'm stopping the broadcast and I'm continuing at the Hangout link that I've just posted.